Something detaches from the missile at 300 kilometers above the Earth. The main booster has burned out. Its job is done. It will tumble back into the atmosphere and disintegrate from heat and aerodynamic stress. But the warhead, the 3.6-meter section at the tip of the Fattah, doesn't follow it down. Not yet, not in a straight line. Because at the exact moment of separation, something inside the warhead ignites, a motor, a small one. Hidden inside the re-entry vehicle itself, invisible from the outside, buried deep within the nose section of a missile that is already traveling at hypersonic speed in near vacuum. It fires. Yes, it fires. And what happens next is the engineering detail that makes the Fattah fundamentally different from every other ballistic missile Iran has ever built, and different from most ballistic missiles anyone has ever built. It fires. And what happens next is the engineering detail that makes the Fattah fundamentally different from every other ballistic missile Iran has ever built, and different from most ballistic missiles anyone has ever built. Most people assume a missile steers the same way an airplane does: wings, fins, aerodynamic surfaces deflecting airflow to change direction, and that assumption is exactly right for missiles flying inside the atmosphere, where air exists to push against. But the Fattah's warhead separates at 300 kilometers altitude. The atmosphere at that height is not air. It is near vacuum. There is almost nothing to push against. Aerodynamic fins at that altitude are decorative at best. To change direction in near vacuum, you need something else entirely. You need to redirect the thrust. That is what the strange motor does. And the way it does it is more elegant than almost anything else in modern missile engineering. We'll get to exactly how it works in a moment. But first, we need to understand why it exists at all, because the problem it solves is not obvious until you understand what a conventional ballistic missile actually looks like in flight. A standard ballistic missile follows a simple arc. First stage ignites, burns, lifts the missile out of the atmosphere at high speed. Motor burns out, warhead separates, and from that moment, the moment of separation, the warhead is a cannonball. Gravity is pulling it toward the Earth. The thin remaining atmosphere is producing some drag as it re-enters, but its trajectory is governed entirely by the physics of the initial launch, the angle, the speed, the direction at separation. Any radar system tracking it from the moment of boost can calculate with high mathematical confidence exactly where that warhead will land. The impact point is determined by equations that Isaac Newton wrote in the 17th century. It doesn't change. It doesn't move. It is, from a physics standpoint, perfectly predictable. And a predictable impact point is a solvable intercept problem. That is why every ballistic missile defense system in the world is built on the same core assumption. If you can track the incoming warhead long enough to establish its trajectory, you can calculate a firing solution and put an interceptor in the right piece of sky at the right moment. The Patriot does this, the Arrow does this, the SM-3 does this. They are all solving the same geometry problem, and they solve it well, against conventional ballistic missiles. The Fattah was designed to make that geometry problem unsolvable, and the tool it uses is that small motor hidden inside the warhead. So let's open the warhead up and look at what's actually inside. The Fattah 1 is 11.5 meters long and 80 centimeters in diameter. The forward 3.6 meters, the warhead section, contains three things: the explosive payload, the guidance system, and the post-boost motor. The explosive payload is a conventional high-explosive warhead weighing between 350 and 450 kilograms, optimized for penetration against hardened targets. The guidance system is a hybrid arrangement combining inertial navigation, an onboard computer continuously calculating position from known acceleration measurements, with satellite inputs from GPS or GLONASS to correct accumulated drift. That's the brains. Now for the part that matters most. The post-boost motor is a solid-fuel rocket motor, not a large one, but it sits at the base of the warhead section, and it has one feature that makes it different from a conventional rocket motor. Its nozzle moves, not randomly, precisely, under command. Here is the physics of how a movable nozzle steers a rocket. When a rocket motor fires, it produces thrust, a force directed out of the nozzle in one direction, which pushes the motor and everything attached to it in the opposite direction. If the nozzle points perfectly backward along the missile's axis, the thrust pushes the missile perfectly forward, straight line, no turn. But if the nozzle tilts even a few degrees, something important happens. The thrust vector, the direction of the force, is now angled slightly away from the missile's center line. That means the thrust no longer passes through the missile's center of gravity. And when a force doesn't pass through an object's center of gravity, it generates a torque, a rotational force. The nose of the missile pivots. The whole vehicle turns toward the direction the nozzle is pointing. This is called thrust vector control, or TVC. It's the same principle the Saturn V rocket used to steer toward the moon, the same principle SpaceX's Falcon 9 uses during ascent, the same principle the Trident submarine-launched ballistic missile uses to hit targets with precision from thousands of kilometers away. The Fattah's post-boost motor uses a movable nozzle attached to the motor via a ball joint. A socket, essentially, that allows the nozzle to swivel in any direction while maintaining a seal against the high-pressure combustion gases passing through it. Hydraulic or electromechanical actuators push on the nozzle from the outside, tilting it on command from the guidance computer. Tilt left, nose goes left. Tilt right, nose goes right. Tilt up, nose pitches up. The warhead can be steered in any direction as long as the motor is firing. And at 300 kilometers altitude in near vacuum, this is the only steering method that works. Aerodynamic fins produce zero force when there's no air to deflect. Thrust vector control works in vacuum because it doesn't need air at all. It redirects the exhaust, and Newton's third law does the rest. But here is where the Fattah's motor does something that separates it from a simple steering system, because it doesn't just steer. It does two completely separate things at the same time. The motor fires for up to 50 seconds after separation. During those 50 seconds, the guidance computer is running a specific burn sequence, a programmed series of lateral pulses and forward acceleration burns that interleave with each other. The forward acceleration burns maintain the warhead's hypersonic speed through the upper atmosphere, where aerodynamic drag would otherwise begin to slow it below the speeds that make intercept geometry so difficult. The lateral pulses shift the warhead's ground impact point, moving the predicted landing location in a controlled sequence throughout the terminal approach. This is the engineering that most people miss. The motor is not simply moving the warhead in one direction to dodge an incoming interceptor. It is executing a programmed sequence of trajectory changes, some of which look like evasive maneuvers, and some of which are fine corrections toward the actual target. From the outside, from a radar trying to track the warhead and compute a firing solution, these burns look identical. The radar cannot tell the difference between a correction burn toward the target and an evasive burn away from the interceptor. It can only see a track that keeps changing, an impact point that keeps moving. And a moving impact point breaks the core assumption of every ballistic missile defense system ever built. Here is what that means in practice for the system trying to intercept the Fattah. A hit-to-kill interceptor, the type used by the SM-6, which is the U.S. Navy's primary near-term defense against maneuvering hypersonic threats, carries no explosive warhead. It wins by physically occupying the exact same cubic meter of atmosphere as the incoming warhead at the exact same millisecond. To do that, it steers toward a predicted intercept point. Its guidance computer continuously updates that point based on the incoming track data from the radar. The interceptor has its own thruster fuel to make course corrections, what engineers call the divert budget. Every time the predicted intercept point moves because the Fattah's motor fires another lateral burn, the interceptor must fire its own thrusters to follow. Each correction costs fuel from that finite divert budget. If the Fattah's motor can force enough course corrections before the intercept window closes, the interceptor runs out of divert capacity and misses. This is not a contest of speed. Both objects are moving at hypersonic velocities. It is a contest of geometry and fuel accounting, and it is engineered specifically so that the Fattah wins that contest. But there is a constraint on this system that the Fattah's designers had to solve. and the solution reveals exactly how precise this engineering had to be. The post-boost motor burns for up to 50 seconds. During those 50 seconds, it is performing lateral maneuvers, but it also needs to arrive at the correct target. A warhead that successfully evades every interceptor and then lands 3 kilometers from the intended target has accomplished nothing strategically useful. So the guidance system running the burn sequence must balance 2 competing objectives simultaneously. Execute enough unpredictable lateral motion to exhaust the interceptor's divert budget while maintaining enough trajectory accuracy to hit the intended target within the claimed single-digit meter circular error. The burn sequence is engineered so that the evasive burns and the aim point correction burns are interleaved. The motor fires evasive pulses that move the predicted impact point around in a controlled pattern. But the pattern is constrained so that after all the evasive pulses are complete, the warhead is still on course to hit the actual target. This is the engineering insight at the center of the Fattah's design. It doesn't need to outrun the interceptor. It needs to exhaust the interceptor while simultaneously staying on course, and it achieves both with a single solid-fuel motor, a movable nozzle, and a guidance computer running a pre-programmed burn sequence that balances evasion and accuracy in the same 50 seconds. Once the post-boost motor burns out, the warhead enters the dense lower atmosphere. Here, aerodynamic fins, which were useless at 300 kilometers altitude, become effective again. Air now exists to push against. The fins provide additional control authority for terminal guidance, allowing the inertial navigation system and satellite inputs to make final corrections toward the target in the last seconds of flight. The warhead is now moving at sustained hypersonic speed on a non-ballistic trajectory that its guidance system steered it onto, approaching a target point that no defense system could confidently predict from the original launch trajectory. The conventional ballistic missile is a cannonball. You can calculate exactly where a cannonball will land from the moment it leaves the cannon. The Fattah is a cannonball that carries its own small rocket and a computer and uses them to change where it will land throughout the descent. That single engineering decision, putting a small motor with a movable nozzle inside the re-entry vehicle, transforms a predictable physics problem into an unsolvable targeting problem. It doesn't require a revolutionary new propulsion technology. It doesn't require exotic materials or new physics. It requires careful mechanical engineering, a precise guidance algorithm, and a 50-second burn sequence that does 2 things at once. Iran's engineers built something genuinely difficult by combining tools that have existed separately for decades in a configuration that most missile programs never attempted at this scale and speed. The Fattah is not the fastest missile ever built. It is not the largest. Its explosive payload is conventional. What makes it difficult is the small motor buried in its nose, the movable nozzle attached to that motor via a ball joint, and the guidance computer running a program that simultaneously aims at a target and moves away from anyone trying to calculate where it will land. The physics of thrust vector control was not invented in Iran. It was developed in the United States and Soviet Union in the 1950s and 1960s for exactly the same reason, steering things that fly in near vacuum where fins don't work. What the Fattah did was apply that decades-old principle to the specific problem of defeating missile defense at hypersonic speed in the terminal phase of a ballistic trajectory, with a motor small enough to fit inside the nose section of a medium-range missile. Simple idea, precise execution, and an engineering problem that every defense system in the world is still working to answer.